Hi students, welcome back to geology. We are now going to start looking at just how does internal Earth work. So now that we know about the layers and we know a little bit about continental drift, now we want to know how things really move. So as you listen to this lecture, I want you to ponder, why might you find the youngest rocks at mid-ocean ridges? And why might that matter for the idea that plates are moving? Okay, so think about that as we go through this. So, first stop, just after World War II, scientists started looking at the ocean floor. And prior to 1947, most people assumed that the ocean floor was flat. Okay, and we talked previously that after Alfred Wegener's theory of continental drift started to become accepted, most scientists just assumed that the continents were plowing through the oceans. And so after this lecture, you'll kind of understand how that's not really how that works. So in 1947, scientists started mapping the ocean floor, and because of World War II, we had the technology to do sonar mapping. Sonar mapping uses a sound wave to send it down to the bottom of the ocean floor, and the boat would pick up on a receiver the return echo from it hitting the ocean floor, and you can calculate that distance and then get an idea of what the ocean floor looks like. Marie Tharp was a geologist that was working on a very detailed map of the mid-Atlantic ridge, which we'll talk about in a second. And unfortunately, she was not allowed on the boat, so her assistant, Bruce Hazen, helped relay that information, and she wasn't taken seriously. And then in 1959, a fella named Harry Hess proposed the idea of seafloor spreading, and he was the one that technically coined seafloor spreading, even though Marie did all of the work. So times are different, obviously. Women are allowed on boats now, but back then it was frowned upon for women to be doing this kind of work. So then the ocean floor was mapped, and what they noticed is that there was topography. It wasn't just flat. In the middle, there was some ridges, and those ridges appeared to have high heat flow and some volcanic activity, which was very interesting. And then based on the thickness of the sediment, they surmised that the ocean floor was actually really young. And it seemed to be producing new material at these high flow volcanic activity ridges. And if that's all new material, what does that mean? So that's where seafloor spreading came in, where Harry Hess finally in 1960 finally produced this theory, where continent and ocean meet at the trenches. An ocean crust is being returned to the mantle at the same rate as being generated at these ridges. So at these ridges is where we have two convective currents, which we talked about in the previous lectures. Two convective currents come up and they pull things apart. Okay, so this is happening under the seafloor. And so these convective cells come up, they pull apart the oceanic plate, and it creates this mid-ocean ridge where new material can fill in that void space. And then that material is then returned to the mantle where it meets the continents. And we'll talk more about that in the next couple of lecture slides. But for now, this is just about the seafloor. The seafloor is being pulled apart, creating this mid-ocean ridge where there's high heat flow, volcanic activity, so new crust is being formed. So as this is all happening, we're also learning about something called paleomagnetism. So scientists started combining various theories together. So we've got mantle convection, continental drift, seafloor spreading, and then this is where plate tectonics started to rise. And one of the final kind of heavy hitters was using paleomagnetism, which is a study or a sub-study of the earth where people are looking at rocks that have iron-rich minerals in them that magnetize to Earth's magnetic field. Earth has a magnetic field that goes out of the South Pole and returns to the North Pole. And this is what your compasses, for example, use. They use magnetic north, or the magnet that is magnetizing Earth. And this is from the interaction of the inner and the outer core. So the inner core is solid and the outer core is liquid. Both are iron and nickel. So you have solid and liquid metals interacting with each other, and it generates this magnetic field. Every 300,000 years or so, the poles reverse. So right now, our North Pole, where all of the magnetic field enters, is at the north end of the planet, and where everything exits is at the south end of the planet, which is the South Pole. And every 300,000 years or so, they flip. Okay. And that creates the study of paleomagnetism, where we can take samples in the field and we analyze them for their orientation. So when rocks are first deposited and they have iron-rich minerals in them, they will align themselves to magnetic north. So they'll give themselves a nice arrow pointing to north, where north was when it was deposited. And what this tells us about seafloor spreading and how this can be used is that we can look at the magnetic anomalies over time throughout the ocean floor. So everything that's happening really close to the ocean, mid-ocean ridge now, those are all aligned with a normal polarity to magnetic north we know today. But if you go outwards in either direction from that mid-ocean ridge, some of them start to reverse and point south. And so looking at these orientations, we can get an approximate age of the ocean floor. And so this is a map of the ocean floor. This is off the coast of North America here. Our mid-ocean ridge in the Pacific is a little bit closer to the continent than it is in the Atlantic. The Atlantic is almost dead center in the middle of that ocean. But here you can see where the youngest material is. And then as you move away from that young material, the material gets older and older. And there is matching patterns on either side. So we used paleomagnetism to study the rocks of the ocean floor, determine their age, and then it revealed that the youngest rocks were at the mid-ocean ridges and the oldest material was at the continents. So that further indicates that everything is being pulled apart at these spreading centers. Okay, so this gave rise and gave really good reasoning as to the theory of plate tectonics. So this theory doesn't have a single date. Somewhere between 1965 and 1967, it was really established that the Earth's lithosphere comprised of a number of tectonic plates. There are 7 major, which we'll talk about in a second, and that they have been slowly moving in different directions for about 3.4 billion years, or 3/4 of the Earth's history. Okay, so these are the 7 major tectonic plates. The map also shows you some of the smaller plates, like the Arabian plate, the Juan de Fuca plate, the Cocos plate, etc. But the 7 major are South America, North America, Eurasia, Africa, India, Pacific, and Antarctica. And Pacific is the largest, although it doesn't necessarily look like that on this map. If you stretch the Pacific Ocean across the globe, it is much larger than a lot of these other plates. Okay, and how do we know where these plates are? Well, we use the seismic network. So where earthquakes occur on Earth, we put a point, and if you follow some of those transects, you'll see that those outlines look a lot like this map I just showed you. And so wherever earthquakes happen, that's where plates are interacting. One of the things that you'll notice is that in the center of some of the plates, specifically the Pacific plate here, there are some earthquakes happening there. And in the next slides, we'll talk about, I think it's the last set of slides, we'll talk about what interplate things, earthquakes and volcanoes look like and what that does. So some final thoughts for this portion of your lecture. I would like you in your notes, describe one piece of evidence that the seafloor provides that supports plate tectonics. Just give me one thing. We talked about a couple of things. How can we prove that plate tectonics is happening based on what we see on the seafloor? All right, I'll catch you guys in the next one. Bye.